Okay, the next trend we have is ionization energy. The trend generally increases towards helium, meaning it takes the most energy to remove an electron from helium. But we need to know why. So the ionization energy is the energy needed to remove an electron from an atom to form a positive ion. So we have ionization energy. Okay, now as we go from left to right, we saw with the atomic radius that there are more protons pulling in. So going left to right means that the atoms are smaller, they've been pulled in, and they hold their electrons more tightly. So it would take a lot of energy, or more energy, to pull an electron from the ones on the left than it would to pull one from the ones on the from the ones on the right than it would to pull one from the ones on the left. Ionization increases this way. Now, as we go from top to bottom, we just talked about the shielding effect. Going from top to bottom means that there is more shielding, so basically less effective pull on the very outside ones. That means that it's a lot easier to remove it from potassium than it is from hydrogen. We remember that francium is the biggest. He's kind of like Santa Claus. He's practically giving away his electrons. It takes very little energy to remove them from francium. Okay, so top to bottom, ionization energy decreases because radius and shielding increase, making the electrons easier to remove. Okay, we are AP Chemistry, so that is not enough. We also have to know about first and second ionization energy. So second, we'll be removing a second electron. It gets more difficult as the proton to electron ratio gets bigger. We see this trend. So if you look, removing the first one actually makes lithium attain a noble gas configuration. You see a gigantic jump because if you try to remove an electron from that noble gas configuration, it will take significantly more energy. Similarly, we have 900 to 1700. It's kind of a lot, but 1700 becomes 14,000. So 1,700 becomes 14,000 after beryllium has become a noble gas. Okay, we see the trend again for boron. It goes from 3,000 to 25,000 once it's become a noble gas, or not become one, but attained the noble gas configuration, meaning it has the same kind of electrons in the same shells as a noble gas. So you have to be comfortable looking at patterns with first ionization energy and second ionization energy. We have a couple left. Electron affinity. This is the energy given off when an electron is added to the neutral atom. Okay, so as we go from left to right, they give off more energy because they get more stable. As we go, everything is trying to be like a noble gas. So giving fluorine an electron actually makes it release a lot of energy because it's more stable. Giving an electron to lithium is kind of like, meh, thanks, but I didn't really want it anyway. So we don't see a big release in energy. So from left to right, giving an electron increases the electron affinity, the energy you get when released when you give it an electron. As we go from top to bottom, there's more shielding and the atoms are getting bigger. It's easier for them to accommodate the electrons. Therefore, we don't see as much release in energy for those. Okay, we have a couple more. Let's fly through them. Electronegativity is the ability of atoms to attract electrons to themselves in a bond. You remember freaking hot fluorine. That's the most attractive on the periodic table for an electron. Okay. As we go from left to right, the nuclear charge increases, the atoms get smaller, they want to attain the noble gas configuration, so all of these things cause the electronegativity to increase. I remember electronegativity is just attractiveness. So you can just tell your friends, my, you are looking mighty electronegative today. Okay, as we go from top to bottom, the electronegativity decreases. There's more and more shielding, so it's harder for them to pull electrons into themselves. Okay, so that's electronegativity. Last two on the periodic table, we have the metals on the left and the nonmetals on the right. So metallic character decreases as we go across, and it increases as we go down. That's because really the main characteristic of a metallic metal is losing electrons. Okay, so we see a decrease in character as we go down. Also, if you're over here, they're nonmetals here, and then they cross the stair step and they become metals. The nonmetal character is the ability to gain electrons from its environment, so nonmetals are up here and really good gainers. These ones with lots of rings don't gain electrons. Last one is reactivity. This trend is actually, well, I'll put this slide up. From left to right in the metals, it decreases, okay? Because ionization energy increases, they're holding their electrons more, it would take more energy to remove it. Metals are trying to lose electrons when they react. And nonmetals are trying to get electrons. So based on all the trends we've seen, we know that from left to right in the metals, they become less reactive because it's getting easier for them to gain electrons to be like a noble gas than it would be for them to lose. Okay, in the nonmetals from left to right, they become more reactive, the most reactive being fluorine. Okay, top to bottom, they are less reactive in the nonmetals because they can't gain electrons as easily when they have so many. And top to bottom in the metals, they are more reactive because they have so many shells, it's a lot easier to remove an electron from them. Okay, we will apply this in class. Thank you.